I'll start the recording now. So start with just we're gonna get into hey, what are you doing? We're gonna get into the quantum optics stuff today, which is really just an introduction to all the weird stuff that happens in quantum. Not so much hardcore biphoton physics or whatever, but like yeah, but we'll start with the review. So Luke.
So last class, we learned about diffraction, and diffraction is an effect where waves get pinched through a small slit, and diffraction is basically just waves bending around obstacles. You can also think of it as like that. So what do the lines in the diagrams represent? So you can think of them as wave peaks, but in general, they represent wave fronts, and that's just a way to depict a wave moving through space. So interference occurs between multiple waves, and one way to get this is through double slit diffraction. So if you increase the width of the slits, what would happen? And what if you increase the distance?
Maybe we can stop talking about the photo of that random guy and instead answer the
What do you
question
mean
Luke
by
asked.
what?
So if you increase the width of the slits, more light would pass through. And if you increase the distance between the slits, then the positions of the peaks would change.
Yeah, and just like a little more specifically, when you increase the width of the slits, your wavefronts are going to be kind of less circular. So you're going to see less interference. They're going to be more sort of parallel to each other. So all the waves you're sending through the slits, the peaks are going to be in line with each other's peaks, and you're not going to see as much actual interference effects. And the same thing is true for if you increase the, it's the same for if you increase the distance and increase the width. You're going to just see less interference because there's less overlap between the constructive, between the peaks and the troughs, and less differences between the two waves.
Yeah, because the diffraction happens because the light is avoiding an obstacle. So it happens more around the edges. Next slide. And we also learned that polarization is the direction a wave oscillates. So is it possible to have a wave that is neither horizontally nor is it possible to have a wave that is neither horizontally or vertically polarized? I hope I'm not echoing and vibrating now. So circularly polarized is one of them. And
Well,
that's when your horizontal and vertical polarization is desynced.
so
But
the to be more specific, actually, circular polarization is a thing and elliptical is a thing, but those are actually just combinations of horizontal and vertical. So the answer to the question is actually no. You can't have light that is neither horizontally or vertically polarized because you can think of it like like think of it like you have a plane with an X and Y axis. If you choose a value of X and you choose a value of Y, you can do any point in that plane, right? It's the same thing here. You can do you can make any combination of polarization with your Y axis of vertical and your X axis of horizontal, whether it's circular, linear, whatever. It's all going to be combinations of horizontal and vertical. That was the key thing. Sorry.
right. And what does the polarization of unpolarized waves look like? Okay, so unpolarized waves are just a bunch of randomly polarized waves added together. So there's not really, you can't really identify if it's vertically or horizontally polarized. Can you guys hear me? I hope. Okay, cool. And reflected and refracted rays, when that happens, the reflected ray is completely polarized. And this occurs at Brewster's angle. And the condition for Brewster's angle is that the reflected ray and the refracted ray are 90 degrees from each other. So what's the formula for Brewster's angle? Yep, you guys got it. 10 to the negative 1 n n2 over n1.
All right. So we're now gonna get into sort of. Can you guys hear me? I think my mic. Okay, it's working. We're now gonna get into quantum optics, which is not like it's not it's not quantum optics in the way that like this book is quantum optics, but it is quantum optics in the sense that it's the foundation of all of quantum mechanics and all of optics that relies on quantum. So this is a really interesting way of setting up the Young double slit experiment that comes from the Feynman lectures. If you guys are familiar with those, it's really my favorite way of explaining it. Is that I haven't really seen it explained like this anywhere else, and it's very elegant and easy to understand here. So let's suppose we have a man with a Nerf gun, not a real gun. Okay, it's a Nerf gun, keep it PG, who happens to be drunk, not as PG, but still, and he's spraying bullets in all directions. Okay, so this Nerf gun is shooting its Nerf bullets here, everywhere, right? And so in front of him is the wall with two slits, that red one and the green two, and a second wall behind that wall that's going to detect the number of bullets at each point. So we can move this detector this way and that way to see how many bullets are going in each along this wall. Basically, it's the same thing as collecting the interference patterns that we saw a few slides ago. If I go back a little, it's the same thing as this. We're trying to collect this pattern, but for the bullets. So we're just counting the number of bullets. Okay. So let's first block slit number 2 and send the bullets through it. What we end up seeing is this red distribution of particles. It should kind of make intuitive sense why. When the bullets are right through the center, you're going to have the most. A little away from it, you're going to have this much because you're going to be sending bullets like that. So do we understand why this pattern is what we see? Give me a yes in the chat if you understand what that is. Okay. So we do the same thing for blocking slit number 1, and we end up with that green curve right there. And it's the exact same logic as blocking slit number 2 from when we block slit number 1. Now we're going to leave both of them open. And because bullets can't interfere with each other, they're not waves, we're just going to, when we leave both open, we're just going to get the sum of both. And we end up with the diagram on the bottom right. Does that make sense why? Give me another yes. Okay, great. So this is basically our particle view. When we send a bunch of particles through two slits, we're going to end up with a combination, literally just the addition of what we'd have from one slit plus what we'd have from the other slit. This is what we'd expect if we have particles. Now let's do the same thing, but with waves. And this is what we talked about last time with the double slit, with the diffraction, with the interference. This is where we know what's going on here. So, I mean, to keep the analogy intact, what we're doing now is we're taking some water and we're dipping our finger in it and just creating some ripples over and over again, right? And then we're going to put a bucket at the far end, or sorry, a cork at the far end that bobs up and down. And the amount it bobs up and down tells us the amplitude of that wave at that point in space, okay? So when we do one and when we do the other, we get the same distributions that we did for the particle view, okay? This makes sense, right? But when we do the combination, these waves can interfere with each other. Like that's what we showed last time. And so what we end up seeing is that interference pattern that we show right here. Okay. Does this make sense what's going on here? Give me another yes. Perfect. Okay. So now so let me get rid of those annotations. So this is the wave view. If we have some waves that are coming into our two slits, we'll observe the interference effect. If we have only particles going in, we'll observe this effect on the bottom right, okay? So that's actually how we're going to define waves and particles. Particles give us this. They arrive in countable numbers and do not have interference patterns, but waves do have interference patterns, but do not arrive in countable numbers. Because if you think about it, what is interfering for a wave? Am I on Chromebook? No, I'm on the PC I built a few years ago. I don't know why I decided to show that. Uh, I built a PC in the sense that I bought the parts and attached them together. So maybe not like I actually built a GPU myself. But anyways, sorry, I got distracted. Stop distracting me. So what we see is on the bottom left, yeah, lock in, guys. On the bottom left, this is our particle view. On the bottom right, that's our wave view. Okay. So now let's think about what would happen if our Nerf gun is a light source, okay? What if we're shooting light particles, our photons, at the wall? What do you guys think we'll see? Wave, see some wave, see both, wave. So when it comes to light, we're gonna see, and we're assuming a primitive technology here, we're gonna see the wave perspective, okay? And it resembles the wave pattern. It's not exactly the wave pattern because in reality, there are countable number of lights that are being arrived. Photons are the particles of light, and we're counting those photons to end up with what looks like the wave pattern, but actually comes from a countable number of things. So it is both. And we can actually do this experiment with electrons. We know electrons are particles. This is something that we've known for that scientists do for a very long time before wave particle duality was even thought of. And the idea of shooting electrons with a gun was also a thing for a very long time. If you just heat up some metal, you can create basically a cathode emitter, which lets you shoot electrons at a target. And when you do that, you end up with this same pattern, okay? So despite the fact that we're using our Nerf gun-like electron gun, which is shooting countable number of particles, we're still getting a wave-like analogy. We're still get a wave-like situation. We're getting wave-like interference pattern with a particle-like emitter. And this is the real heart of wave-particle duality. Electrons and electromagnetic waves, which are just photons, behave as both waves and particles, when in reality, by everything our classical logic, our real-world logic tells us is possible, that shouldn't be a thing. That should be should be contrasting perspectives. So do we understand that in the sense that do we understand why that makes no sense? Oh, what? So okay, let me backtrack a little. We're seeing the wave-like interference pattern when we use the electrons or the photons for this experiment. But we collect this pattern by counting the number of electrons or photons that are detected. So we're having the particle-like view of counting with the wave-like view of interference. So what's going on here? That's a really good question, Benjamin. And that's exactly what I asked when I first learned about like this whole Young double slit experiment. Because I was like, I mean, like where does it end? We see this on this photons and light are very small, right? But in the real world, we don't see that. And if you guys are familiar with the Heisenberg uncertainty principle and even the value of Planck's constant, that's actually the length scale, kind of what of where these things happen. If and there's been like massive theoretical physics papers published about this, where if you increase the value of Planck's constant by like a factor of 20, then I could throw this book at a double slit wall and I'll get interference effect of this book. It all depends on the value of Planck's constant, which is the scale at which these things happen. And physicists have actually been able to reproduce this Young double slit experiment with actual molecules, not even just electrons, not even just atoms, but real molecules, which I think is kind of incredible. Like this, us almost approaching things we could get close to seeing. Do Control Shift QQ. No. Okay. So let's get more into why that's weird. Uh I'm not on a Chromebook. Why do you guys think I'm on a Chromebook? Okay. Can we focus, please? Thank you. So this is really weird. I mean, it makes no sense why this happens, right? So it implies that the particle, our single electron particle, is somehow going through both slits and then interfering with itself. Let's try to really figure out what's going on here, okay? So let's place a light bulb behind our slits so that we can like watch where the electrons are going. See, is the electron going to the top slit or is the electron going through the bottom slit? Okay. When we do so, we see half of the electrons go through the top and the other half go through the bottom. This makes sense, right? Our gun's firing randomly in all directions, so half of them are going to go through the top, half of them are going to go through the bottom. But to our dismay, the interference pattern is now gone. Once we've seen the electrons as particles, once we've observed them to be going through either the top or the bottom slit, we no longer get an interference effect. We get that original distribution on the left right here. So that's really weird. Just by observing these particles, just by actually looking at the electrons, we've now broken up the interference pattern. The wave particle duality appears to be gone now. If we decrease the brightness of the light and start to no longer be able to see the electrons once again, the interference pattern comes back. That's really weird. We've proven that just by looking at the electrons, just by observing these particles, we take away the quantum effects. That is the basis of Heisenberg's uncertainty principle, right? You might be more familiar with it as a relationship saying we can either be certain in position or we can be certain in momentum. And that's really what looking at a particle does. When we look at a particle, we get full certainty in its position. And so then we have to have complete uncertainty. Let me not get into that actually. The point is, when we observe this, we collapse the electron wave function. And it's fundamentally due to the Heisenberg uncertainty principle. If you're curious about the real details of why that is, you can go win a Nobel Prize and understand that. So the fact of the matter is, this is one of the wave function collapse is one of the largest standing questions in quantum mechanics. It's honestly like it's an incredible result. I mean, it makes no sense why this happens. And I mean it's I don't know. I'm always amazed when I read about it. It's just like it's incredible. So that is going to be our discussion of uh, the Young's double slit experiment. And actually, we have enough time. I might be able to show some extra stuff for that. But now we're going to talk about quantum entanglement, which is a marginally weirder effect, but also it kind of makes sense when you actually think about it, unlike wave function collapse. So suppose you have two particles, okay? These particles can, oops, these particles can be in one of two states, okay? Circular or square. So basically they have a 50% chance of being in either of those two states, okay? So imagine what's a good analogy? It's like think of your particles as a coin. If you flip your coin, it can be either heads or tails, and your other coin can also be heads or tails, okay? So system one is going to be particle one here, and system two in this diagram is going to be particle two. Since each of them have a 50% of being circle or square, you have a 25% chance for each of these combinations of circle, circle, square, circle, circle, square, and square, square. Does that make sense? Hey guys, focus please. Can I get some more yeses to make sure it makes sense, or some no's if it doesn't make sense? Okay. 75% of them. This is true. Uh, yeah, that's a true statement. So if they are entangled, the probabilities are not what we'd expect, okay? So this system one, this particle one, has a 50% chance independently of being circle or square. And same for system two, 50% chance of being circle or square. But when they're entangled together, they can only both be circle or only both be square. The probabilities when you combine them deviate from what you'd expect when they're not combined. That's what it means for these particles to be entangled. And there's really like deep statistical paradigms that'll go into actually why that like they give you a threshold. There's a CHSH inequality is the big one. And then also, I mean, Bell's inequality is the famous one. Okay, guys, can we stop just drawing ASCII wave art in chat and please focus? Thank you. So let's walk through that in an actual experiment. This is an experiment I actually got to do last semester for one of my classes, and it was like it was really fun. So I wanna show it. But I mean, ignoring how complicated this diagram looks, let's just focus on only this part right here. So we block. Who are people saying hi to? Okay, please can we focus, guys? Uh, we're gonna block the left part of this diagram, and we're gonna to kind of ignore everything that's going on there. All that is a laser. That's all I'm gonna say about that. The thing boxed in blue takes that single laser input and turns it into two lasers. This is called, if you're interested, the process is called spontaneous parametric down conversion, which is a fancy way of saying I take my apple and I cut it in half. That's all it's doing. It's cutting your laser beam in half and making it into two new laser beams, okay? So we can then measure the polarization of these two entangled laser beams, okay? So to be clear, this thing boxed in blue takes an input laser beam and turns that laser beam into two entangled laser beams, okay? It's not like a beam splitter. That's a good question. It's not a beam splitter. Spontaneous parametric down conversion occurs in these really fancy crystals called BBO crystals. Things like boron, borohite, boroxide, something like that. They occur in these fancy crystals, and because of the properties of the crystal and how it interacts with light, it's able to take a photon input and half the energy of it to turn it into two new photons. So you have one photon with energy 10 joules that exits with a photon, two photons of energy 5 joules. But it's not like a beam splitter because a beam splitter preserves uh, other properties of it. So yeah, that's a good question though. It is very fancy and also very expensive. Uh, so we take this beam on the left. Let me get my annotation. We take this beam right here that I'm circling and polarize it entirely horizontally. We then take the other beam on the right and measure the polarization of this beam, okay? So if they aren't entangled, what do you think we'd observe? Like what would our measurements of the polarization on the guy we're measuring be? One horizontal, one vertical. Uh, so okay, maybe I'm not clear about exactly what we're measuring here. We're taking this beam right here, the beam number one, and we're making it entirely horizontal. We're not doing any measurements on this beam. Then on this second beam right here, this is what we're measuring, okay? We're going to only measure this beam and the polarization of that beam, okay? What? Okay. So yeah, what Toby said, what people are saying now is correct. We're going to see the beam be 50% horizontally polarized and 50% vertically polarized. This makes sense. This is like exactly what we should expect because the beam came in right here before we even done any entangle, before we done anything fancy. It has a 50% chance of being vertical, 50% chance of being horizontal. We do something to beam one, but beam one has nothing to do with beam two. Beam two is entirely independent. They aren't entangled. So when we measure beam two's probability of being horizontally polarized or vertically polarized, it'll be the exact same as what it was initially. 50% vertical, 50% horizontal. Does that make sense? Okay. It makes 50% sense. Do you want me to go over it again? Okay. Yes. Full sense. Okay. We have a lot of time, so I can go at the very end. I can go back and review if we need to. But so if they are entangled, what do you think we'd observe? When they are entangled, what do we observe? That's right. The wave is always 100% horizontally polarized. Somehow, when we do something to this beam right here, when we polarize this beam that I'm outlining in green fully horizontally, the other beam also gets horizontally polarized, even though it's entirely like that we're not doing anything to that beam directly. That's because these beams are entangled. That is the basis of quantum entanglement. Somehow, forcing one beam to be horizontally polarized made its entangled partner also horizontally polarized. And this is a really useful property of light that is actually at the heart of quantum computing as well, and even quantum communication. What is interesting about this is that this idea, I mean, there's nothing traveling between these two waves, right? It's not like there's light going from the polarizer of this wave right here to this wave right here. There's nothing traveling between them. So in theory, in principle, does that mean this travels like instantly at this, not even at the speed of light, literally instantly? What's the answer to that? Does it travel instantly or does it travel at speed of light or speed of sound? How is that information of the one beam being horizontally polarized carried to the other beam? Because it somehow has to be transferred, right? What's the answer? Speed of light is a good guess. The actual answer is we don't know. It's kind of a trick question. That's an ongoing area of research when it comes to quantum entanglement. But the fact of the matter is, in theory, it could be larger than the speed of light. And that's really shocking to me at least, because when you think about the speed of light, it's supposed to be a hard limit. Nothing can be faster than the speed of light. But for those of you guys who are familiar with how dispersion works as just the relationship of general wave physics, you can have things called a phase velocity that are higher, or sorry, a group velocity that are higher than the actual speed of light. But that group velocity carries no information. The fact of the speed of light, what it really means when we say the speed of light is a hard limit, is that information cannot be carried faster than the speed of light. You can have just a whole bunch of nothing that travels faster than the speed of light, and that's fine because it's nothing. But an actual something cannot travel faster than the speed of light. That's a kind of abstract way of thinking about it, and it's a lot easier to understand if you understand dispersion physics. But my point is, this is a very interesting fact that without ever transmitting any information directly between these two beams, we're able to force one beam to be exactly the same as the other beam. And as you can imagine, there's infinitely many applications of this, most obviously to quantum computing. but even in biphoton physics. How do two things become entangled? That's a good question. So I can actually just show you. Beta barium borate, I was wrong. When I say BBO crystal, it's literally just like one of these things. It's a small prism that you can just send some light through, and then it does what's called spontaneous parametric down conversion. Okay, so let me also find out. I didn't plan on discussing this, but we have time, so might as well. Oh, did I not record? I am recording. Okay. Uh, I'll send the recording out after the meeting, Toby. Um, so all it does is this right here, where we take that input blue arrow, our crystal, which is also called a nonlinear chi-square crystal, that's the same thing as what I've been saying, BBO crystal, and it turns it into two of those red arrows. For all and for our purposes, it is magic. Like this is some almost it's not really even physics, so to say. It's kind of chemistry how this happens. But it's actually a very, very cool process that I would love to talk about more if I understood it more. Um, oh, so that's actually really all the quantum optics content I had to cover. I did not anticipate getting through this nearly as fast as we did. Does anyone want me to go over anything that we discussed again? Yeah, when it goes through the crystal, it becomes entangled because you, they and the that's oh I see what you're asking now. We're sending one laser beam into our crystal. Let me draw this out actually. So we have our red crystal right here. That's our BBO crystal. BBO. And we send our laser beam into here. Our BBO crystal does some magic, and then it outputs two laser beams, okay? And because these two both come from this, I think I'm flash my code. Because both these two laser beams come from the same input laser beam, that's what makes them entangled when they go through the crystal. We do our unentangled measurements by just using two independent laser beams. This blue box thing also has the capability of just producing two laser beams that aren't entangled. What does it have to do with dispersion? So dispersion, let me show you dispersion versus phase velocity. You guys are probably familiar with dispersion in the sense of it's something where like light becomes all its colors when it goes through a prism, right? Is that what we're thinking of dispersion as? Yeah. So when I say dispersion, I mean something more general. That's part of what dispersion is, but what it actually is, this is probably a good animation. If you guys can't tell, I'm completely winging this right now. I did not plan on talking about this, but interesting at least. So basically, waves in general, this is what this diagram is showing, are composed of many different components, okay? If you remember when we talked about how waves interfere, they can be all these resultant waves, which is that red wave in the back, are combinations of different, more simple waves. Because that wave in the back is more complicated than the waves in the front, right? That makes sense? Okay, I mean, the point is, I mean, so you see how it looks like they're sort of on the back. It looks like there's a wave traveling through that back wave on top of the waves within that wave itself. Do you see what that looks like? Do you, yeah, I'll go back over the collapse again, but real quickly, do you guys see how that wave is moving through the back, kind of? That's called the group velocity. And that group velocity is basically just an optical illusion. There's no actual information carried by that wave, which is why it looks like it's moving so much faster than all these resultant waves. In reality, group velocity, phase velocity are like the fundamental ideas of dispersion. But yeah, this is great. Thank you, Toby. So you can see how you have all these independent waves that are traveling, but you also have what appears to be a group velocity. So the big idea that I'm trying to get at is this group velocity can be faster than the speed of light, but it carries no actual information. The details of dispersion aren't important. because honestly that needs a lot of background. So yeah. Wave function collapse. Let me go back there. So if you remember when we got to this point in the slides, we had set up the fact that the idea that a particle can go through two slits and interfere with itself is very strange. Can we agree that that is very strange? Give me a yes if we can agree that that's strange. Okay. So what we then do is we're gonna place a light bulb. So if I draw the situation, we have our device that's producing electrons that go in all these directions. Okay. And then we have our two slit guy right here. And we're gonna put a guy right here that's gonna watch the electrons as they go through, right? And he's gonna see, okay, I see some electrons going through the top. Oops. And I see some electrons going through the bottom. Okay. This guy is watching where those electrons go, and he is counting the number of them. Okay. But then when he does that, he sees that what we end up with is just the addition of those two wave profiles, like we showed back on this slide right here on the left. He observes the left, not the right, when he would expect to observe the right, because that's what he saw when he wasn't staring at the particles as they go through each of them. So if this guy isn't here, if I get rid of him, we no longer have particles going through each of these guys, okay? What we actually have is the electron wave function traveling through these slits, okay? Wave functions in physics are kind of a weird concept to wrap your head around at first, but all it's saying is that the electrons are no longer, they're not a single particle in space, they're now an actual wave function. There's actually probably there's just one diagram I saw a while ago of wave function collapse diagram. Uh, yeah, this is perfect. Okay. So what we have before, I don't know what GRW is here, but this is like on the top is when he's not staring at the particle, okay? The top is when the guy is just seeing the interference effect. He's like, what's going on here? We have a full wave that's like goes up and down and side to side, and it's really weird. But then when he does stare at the wave, when he is looking at what's going on, the wave collapses into a single state, okay? It's no longer this weird shape of everything that's going on. And in fact, it's not even going to look like this. It's going to look like a single line that goes up and then goes back down and continues. Because we've collapsed it into literally a single particle. Wave function collapse is just literally the process of going from a wave to a particle. That's what it is here. In reality, it's a much deeper thing with many more implications. It is exactly like Schrodinger's. Now, here's the thing. Schrodinger initially, when he made up GRW, is the only precisely proposal for a quantum theory that postulates dynamics of what is known. Okay, I mean, that's just like theoretical physics nonsense. They're just making up words so they can get a grant and get their paycheck for the year. But like, the point is, um, what was I saying? Um, what was I saying before I started talking about the theoretical physicist paycheck? Oh yeah, Schrodinger's cat. Schrodinger initially made up Schrodinger's cat as a mockery of quantum theory. He's like, you mean to tell me a cat can be in this box and is either dead or alive until I look at the cat? He made it up to make a joke about quantum mechanics. But somehow people have come to accept it as a description of what actually happens, which I think is pretty funny. But it is exactly like Schrodinger's cat, probably to Schrodinger's dismay. Does that make sense? The wave function collapse. Anything else anyone want me to go over again? These two things, this idea of wave particle duality from Young's double set and quantum entanglement are, in my short experience with quantum optics, the two most important things to understand to get started in quantum optics. Obviously, there's more complicated effects, and there's like the world of quantum optics is very cool and very broad, but these are at least like the two most important things that I would say you should know. And I mean, I would honestly be like, I would give you $5 if you found a Siley test that mentioned quantum entanglement. It is extremely unlikely that a Siley test mentions quantum entanglement. So this
It
much is
won't.
true.
It's against the rules.
They can't at all, bruh.
They're not allowed to ask anything about quantum
Like they say you
optics. They're
yes.
allowed to ask you things about the energy of a photon, and that's just about as far as the quantum world goes in the Science Olympiad optics test.
Well, there you have it.
Actually, let me look at what
Well,
I
actually, when it
want
comes to the
there.
when it comes to the photon energy, there is something that you could point out here. When we input our laser beam into this guy, if it has energy 10 joules, these two laser beams right here are gonna have energy 5 joules. Okay, because we're conservation of energy has to be held. So there you go. This does relate to Siley
Yeah,
and will certainly come up.
Cornell tests suck. I don't know what you mean. Also, there's polarization. Polarization is absolutely legal, but
Billy kind of said this.
only as far as cosine squared rule goes and 1/2 rule.
I asked about this on the trials test that I wrote for Carmel. So
Yeah.
taking a
No, calculus
derivation,
is not allowed in Science Olympiad, unfortunately.
much
I
much to my dismay.
I wrote a test, an optics test actually, for Captain Summer Exchange this summer, and the one question that had calculus, because I asked to derive Snell's law with Fermat's principle, it got flagged and removed. They made me remove it,
They
and I was
have
very pissed about that. But it's
wait, they
okay,
have
'cause
flagging algorithms?
well, no, someone reviews your tests.
Oh,
So some Mason guy who placed 25 places under. Silly guy.
silly
Um,
guy.
yeah, silly guy. But
Oh,
they, yeah, they instead I'm just gonna have them derive it with Huygens, which is a little bit more sad, but yeah,
I put calculus on this test and no one got this question right, sadly. But
wait, which one is this?
this is soaps from
Oh,
this
I
year.
took that test. That was miserable.
Oh, that's my bad.
Wait, is this the wait, is this a drop one?
This
I
is
wrote I wrote a question like that literally on my test.
oh
And also that's a USFO question.
I did not get it from the
Physics
USFO
Olympiad.
test. I got it from my
Oh,
homework.
oh wait, yeah, I heard one of the questions for Yusufo this year was optics.
Yeah, but
Just
for this year is different. It was just basically the a lens system.
yeah, I heard about that because I have a friend who took it and he didn't do so well, and he was like, "Yeah, if you took it, you probably would have like placed just because there was optics." Unfortunate.
So does anyone so this is gonna be the last content lesson that we do. Next class is gonna be uh review and activities of all sorts. So does anyone have any questions about this lesson or about any of the previous lessons that we've had that you would want us to go over just for just to help you kind of understand what's going on? Literally anything if you would like us to cover one more time.
UNA.
How do you go from 1 joule to 5 joules? So first of all, joule is Joule. And then what do you mean 1 joule to 5? Oh, do you mean um right here? You can fill out the attendance code now. It's the convex 8 would be the attendance code. Maybe re-explain the derivations. All right. So they enter with 10 joules, not 1 joule, 10 joules. And then these two are going to be 5 joules. Okay. It just gets cut in half.
It's a quantum beam splitter.
Yeah. I mean that's what it is. So I'll give you 1 minute to fill out the attendance code, and then I'll go back to that first
Oh,
lesson.
Ishan, I think we have to give them time to fill out the end of the year feedback form,
Okay, well
which
then
should take a couple minutes, like
let
7 to
me
10 apparently.
let me do this then. Let me go back to the derivations,
Here, I'll find the feedback form,
and then
and
here,
then
yeah, perfect. So this is what caused a lot of confusion the first time. Let's just revisit this just to kind of see if we have more of an understanding of what's going on now. So if you remember, let's focus on this diagram on the bottom right. We're setting up reflection. We're trying to derive the law of reflection. So we say this distance right here is x, and then this large distance right here is d. So then this distance that I'm boxing is d minus x. Our light starts at the point A, reflects off that middle line, and goes to point B. And we're trying to see the relationship between the angles alpha and beta. So to do this,
Right.
we just do, oh, this is relevant. We do a little bit of finagling. So first we set up our Pythagorean theorem expression, okay? L equals the square root of x squared plus a squared. That's this triangle that I'm doing in red, okay? Oops, that's not what I want to do. L equals x squared plus a squared, okay? And then it also travels on the hypotenuse of this triangle right here. So you add d minus x squared, that's this bottom leg, plus b squared, that's this side leg, to get the hypotenuse. That's going to be this. And so the total path to green is going to be here up to here. And that's going to be this full expression, okay? Does that part make sense? Do we remember this? Perfect. So then this is the part that everyone was confused about, and that I will remind you does not matter how we get to this expression. What this is saying is
just to say, like, people don't complain about the calculus. We're explaining what it does. You don't have to understand how the math of the calculus works. You don't need to. This is conceptual. Just trust us with the calculus and don't complain about it.
and the fact of the matter is, like, when you do calculus in physics, I've only had to do integrals and derivatives in my math classes that I've done in college. I had a teacher last semester who said, if you show like taking derivatives and integrals on your work, I will take off points. He wants us to not show work and just do this with the computer. He really, like, it is completely irrelevant how we get these expressions. Like, it's useful in the sense that it helps you understand the math, but ultimately it doesn't matter. Toby, if you want, you can email us about it and we'll explain it, but it's not the most complicated thing. It's a pretty somewhat basic derivative. But the point is, we take the derivative. So what this is saying is this dl dx is the rate of change of L. And so when we find when dl dx is 0, if you think about like a parabola, when the rate of change on the parabola is 0, we're finding the minimum of the parabola, which is to say that we want this expression that I'm going to box in pink. We want this pink expression to be equal to 0, okay? That's the goal. So aside from all the calculus and extra stuff, we want the pink to be equal to 0. So before doing that, we do a little bit of a cheat to get this in terms of alpha and beta. If you remember, sine is opposite over hypotenuse, right? SOHCAHTOA. So for alpha, the opposite is going to be this length right here, which is equal to x, okay? And the hypotenuse is going to be square root of x squared plus a squared, which is what we have right here. So this guy right here is equal to sine alpha. Similarly, this guy right here is equal to sine beta, because this length right here is d minus x, and this length right here, the hypotenuse length is going to be square root of d minus x squared plus b squared. Do we understand that? Sine alpha minus sine beta equals dl minus dx. Give me a yes if we understand. Why the minus? The minus comes from when we take the derivative. That's just part of the math. Because if you see this
For
plus
those
turns
who want
into
to
a
get,
minus right there.
yeah, for those who want to get technical, it's because of the chain rule from the d minus x, which is taken as a separate function.
So we said 0 equals sine alpha minus sine beta. which means sine alpha has to equal sine beta. And since in this situation, alpha and beta must be less than 90 degrees, alpha has to equal beta. And that's our law of reflection. Do we have at least a little better understanding of how this worked than we did on day one? I'll be happy if that's the case. Perfect. And I'm a happy man. I'm glad to hear that. I'll real quickly show the refraction one, which I think is on here. Yeah. So just oops. So this is the same thing, but the key difference is that we're now dividing by V1 and V2 to include the fact that the index of refraction is different. Other than that, it's basically the exact same derivation. So these slides were made available to you a while ago in Google Classroom. Yeah, V is velocity. And so if you'd like to look at them again, it's there for you. But other than that, that's all I have to say about that. If you guys haven't filled out the form yet, go ahead and do that now. Otherwise,
If anyone wants a fun exercise, if you want to try deriving the critical angle formula, you should give that a try. It's a very fun exercise.
this is the attendance code. Compensate, I think. Wow, I'm very impressed, Toby.
Amazing. I'm sure everyone remembers chat, Toby. Yeah, we need code bring back code Lukey Pook. Bring it back.
Make
Do you
the
guys have
last
any
one
questions
Looky-
about anything? Sorry.
no, make the last one Looky Poop 9.
We are not answering that question.
Bring back Looky Poop. Bring back Looky Poop.
We don't decide the attendance codes actually. So we don't have a choice. Begs a hedge.
Guys, then give me the Discord.
Make sure you guys fill out the form.
Yeah,
I
make
don't
sure
want
you
to get
fill
an
out the form.
angry DM from someone. If you're not filling out the form, you should
Yeah.
not fill out the form.
We can see who doesn't fill out the form, so we will find you guys if you all find the form. No, I'm not checking right now. Maybe. I just had to check. I don't know if the response are getting sent back to us.
Yeah, not
Wait.
yet.
But-
please.
But either way, you should always just be honest.
Wait, for the feedback form, it tells you to like film an impression of your instructor, of one of your instructors, but then it tells you to
Feedback is
submit a
nice.
video, but it's like a text answer.
Yeah, seems
You
competent.
put the URL.
We didn't make this form, so we have no idea
Yeah.
about any of this. Because this they keep like the feedback stuff confidential, or your name's confidential or something like that.
Yeah.
So, which also means you can insult us as much as you want.